now we get to cohomology. And this is going to be specifically cohomology of manifolds. It is possible to do cohomology of topological spaces in general, but I would say this is perhaps a little bit too abstract. Maybe it is not appropriate for a first course in algebraic topology. But also, I wanted to put a lot of emphasis on manifolds because they are a very important part of topology, and to put a lot of emphasis on differential forms. They're not just important in topology, they're important in other areas of mathematics as well. So there's that extra added benefit of learning this kind of material that will help you in your future math journey. So that's why we're only going to do cohomology of manifolds, but you should understand that it is possible to become a lot more abstract and do cohomology of what are known as topological spaces. And this stuff with cohomology, it just gets more and more and more abstract. Then one can do something called sheaf cohomology that was introduced by Grothendieck, and then you just go crazy with it. But we're just going to do cohomology of manifolds. And it would be helpful to do a quick recap of homology. This is homology of topological spaces. And the way we do this is we start with a topological space, X, and then we construct something known as the chain complex. So the chain complex is you have 0 chains, you have 1 chains, you have 2 chains, 3 chains, and then you have descending maps. When you reach the end, you just map it to 0. Right? That's what you just do at the very end. You call these maps del. We call it the boundary map. This is just, of course, the 0 map. And we have to recall what these C's are. So C n of x, this is the free group generated by continuous maps from the n simplex into X. And I should say this is the free abelian group. Free abelian group generated by these continuous maps. Now, we did also remark, and this was convenient when we talked about integration, it is possible to modify this theory a little bit and to replace simplices by cubes instead. And by that I mean, of course, the interval from 0 to 1 to n. Right? You could call it maybe with a square or something. And if you do that, then defining the boundary operator is a little bit trickier with the notation. And then you have to make a special exceptional case when you go from 1 to 0. You have to sort of treat them exceptionally. But to be consistent with notation, mathematicians realize that when you're doing homology, this is more convenient to use the notation of an n simplex. And this is the way you define these. These are called n chains in X. We're not going to go over how the boundary operator is defined, but this is what we have. And what we should recognize is that, in general, these groups are not finitely generated. So these are not finitely generated abelian groups, for the simple reason is, how many different mappings can you come up with? Like, for instance, let's say X is the real line. How many maps do you have from the 1 simplex to the real line? You have an infinite number of these. You can, well, I don't think I have to say more. I think you believe that. You can come up with an infinite family, an uncountable collection, perhaps even. So there's a lot. So these groups are not finitely generated. They are free groups, but they're not finitely generated. And then we define, and then we realize that d squared is equal to 0. Okay, we realize this. And then the way we define the n homology group, it's the kernel of the outgoing map on the nth level, and we mod out by the image of the incoming map from the higher level. Because of this relationship, the image is a subgroup of the kernel, and so you can talk about the quotient. And in general, the kernel, so in general, this is also not finitely generated. And the image, in general, I mean, you can come up with some degenerate cases when it is not finitely generated. Actually, before I go on, this is actually the reason why we talked about simplicial homology, the homology of a simplicial complex. Because in that case, the chains of a complex, those actually had a finite number of generators, which made it an easier problem to figure out what the groups are. But for a topological space, you have an infinite number of generators. The kernel is not necessarily finitely generated. The image is not necessarily finitely generated. But something really cool happens that when you calculate the quotient, then what happens is that Hn of x for many spaces that we care about is finitely generated, is a finitely generated, and it's an abelian group, finitely generated abelian group. Not always. You can, again, come up with examples where it's not finitely generated. For instance, like we know that H0 of x would be isomorphic to z to the k, where k is the number of path components of x. So if you have a space with an infinite number of path components, then this group would not be finitely generated. It will have infinite rank. So it does not have to be, but for many spaces that we care about, the kind of manifolds that we looked at, spheres and all that stuff, wedges of spaces, things like that, it turns out being finitely generated. So that means you can actually understand it in some kind of reasonable way. And this is what we call homology. Okay? So now, what do we do with cohomology? So with cohomology, we're going to start not with a topological space, but we're going to start with a manifold. And in fact, this is going to be a smooth manifold. And I want to say this again, it is possible to define cohomology for topological spaces in general, but we do not want to go there. So you start with a manifold, and you're going to construct not a chain complex, but we're going to call this a cochain complex, because the maps will now go in the other direction. And you're going to change these. Yes, you're going to just change all of this. And this is going to be omega 0 of x going into omega 1 of x. And notice everything is now going up. Omega 2 of x, omega 3 of x. And at the end, you just put a 0. And the name of the map that goes up is called D, the exterior derivative. And it satisfies the same property that we talked about before, d squared is equal to 0, though for a different reason. Here the reason is because of the mixed partials theorem. Now, what are the forms here? So, recall that omega n of x is equal to, now I should say that I'm not saying what the dimension of this manifold is, because it's not going to be important in what we do. So the n here is not referring to the dimension of the manifold. This manifold has a certain dimension, whatever it is. Let's not give it a name if we do not need to give it a name. So then omega n of x is equal to, this is by definition, these are n forms on X. But what is an n form? An n form is a collection. This is the way we're doing it. I have to caution you that if you're reading Braden or you're reading another book, no, if you're looking at the Bott and Tu book on differential forms and algebraic topology, then what the definition that I give is sort of closer to what they have. That a form, a differential form on a manifold, an n form, is a collection of forms. So maybe because this is a smooth manifold, it has an atlas. So it's X comma an atlas. Okay, and an atlas is a collection of functions. It's a set, it's a collection of functions. You have some indexing set. I kept on calling the index set lambda. So you have some indexing set. And you have mappings. So these are maps from some Euclidean open set. Now usually we write, let's say we call it phi lambda. And I know I always write something like r to something into X. There's a dimension here, but maybe because I do not want to emphasize, I do not want to give a name to the dimension of the Euclidean space, maybe I'll just call it U subscript lambda, where U subscript lambda is some open set. It's an open set in some Euclidean space, the dimension of which we do not care about. It's just an open set in some Euclidean space. That's all it is. I know that we usually assume that this is R to some power, but more generally, you are allowed to assume that the atlas is defined on Euclidean open sets more generally. Okay, so these are mappings. They map this Euclidean open set homeomorphically onto X, and it satisfies all of the properties. So an n form would then be a collection of Euclidean forms on each of those charts, Euclidean open sets. So it would be a collection of omega lambda, where each omega lambda is an n form on that open set. That's what that is. And this collection, it's coherent. And this collection is coherent. I'm not going to say what that is again, but we've talked about that before. So that's what it means to be an n form. So I just want to keep on reminding you these definitions because it's easy to forget them, and the difficulty here is always in the definitions. The most important point here to understand, the way we're doing it is forms for us are not actually defined on the manifold. They're technically defined on the charts of the manifold. So you bring them back to Euclidean space in which we're comfortable. And then we do all of our calculations in coordinates. These are called coordinates. You think of these U lambdas as being coordinates. So you're doing calculations in different coordinate systems. Okay, so that's what it means to be an n form on X. Now, previously, when we talk about homology, we said that these are groups. In this case, so maybe I should say this. So observe that omega n of X is a free module over, so I'm about to say some stuff which is highly algebraic, and if it does not make too much sense to you, if the terminology is unfamiliar to you, you will be able to ignore it without any kind of harm. So it's not that big of a deal, but maybe you find it helpful for me to go over this vocabulary again. So omega n of X, this is going to be, so when we talk about homology, we say it's a free group, a free abelian group. But here, this is going to be a module. A module is sort of like a vector space, but coefficients are smooth functions. Because every single one of these forms, an n form is a collection of forms. And forms, if you recall, they're formal symbolics of differential symbols, but the coefficients in front of them are smooth functions. So this is going to be a free module over smooth functions. Okay, of rank of a certain rank. I mean, maybe it could be, well, that could be a more complicated question whether it's finite rank or not, but let's just say this. Often a finite rank. So maybe I can also say this. So, so often the rank would be equal to, it would be the dimension of the manifold choose n. It's basically how many differentials can you choose. If you have a manifold, basically this, if you have a manifold of dimension 3, then that means all of these are going to be, so let's say the dimension of the manifold is 3, and you're interested in 2 forms. Then that means that every one of these Euclidean open sets, these are going to be open sets in R3. And the differentials that you pick, you can only pick 2 differentials out of 3 in every single one of these. And then the idea is that because this is a coherent collection, if you know what happens in the single chart, often, though not always, but often you know what happens in every other chart, right? Because when the charts overlap, if you know what the form is doing in one chart, you can often figure out what it's doing in the other chart with which it overlaps because of the coherence condition. And so this is what you would have. So it's finite rank. So often that's what's going to happen. However, omega n of x, now you have to understand that smooth functions, these include that, to abuse notation, you would say that the real numbers are a subset of smooth functions. Now, technically what we really mean to say is that the real numbers embed into smooth functions, because every real number can be regarded as a constant function defined on the manifold, and a constant function will be smooth. So if you look at this as a module over the real numbers, then this would be a vector space. However, n-forms over R as a vector space, so this is what you're used to. Maybe you're not used to this language of modules. Maybe this is very new to you. But when you consider n-forms over the real numbers as a vector space, this will usually be an infinite dimensional space. And if you're confused by that, and you're thinking to yourself, how can it have an infinite number of dimensions if there's only a finite number of choices for how you can pick the differentials without repeating them? That is true. There's only a finite number of ways to do that. What you need to understand is n-forms are not just choices of differentials. They're also, the coefficients are smooth functions. So how many smooth functions can you have? Well, in general, there's an infinite number of smooth functions that you can define on a manifold. So for that reason, the list of all smooth functions on the manifold, that is an enormously large collection of functions, and you cannot find a finite basis for that. The reason why you can do it here is because the smooth functions themselves are being used as your coefficients, and the basis is then on just the differential choices. But when you consider it as a vector space over the real numbers, the coefficients are not necessarily real numbers. The coefficients are now possibly smooth functions. So because of that, there's too many choices, and it's will in general be an infinite dimensional space. So it's kind of similar to what you have with homology, that the n chains are infinite rank as an abelian group, and the n forms will have infinite dimension as a real vector space. However, when you look at the quotient, when you take the quotient, what will happen is you'll get something that is often finite. So we define h uppercase n of x, and this is called the nth cohomology of x. So this is by definition. This is how we define it. And it's exactly what we did above, that you're going to look at the kernel of the outgoing map. You're going to take the kernel of the exterior derivative from n forms to n plus 1 forms, and you're going to mod it out by the image of the differential operator from n minus 1 forms into n forms. Very similar, except there's this change in notation between n plus 1 and n minus 1. But other than that, it's very similar. And so this will, in general, be infinite dimensional. This will be, in general, infinite dimensional. However, the quotient, it turns out, as we will see, the cohomology is often finite dimensional. So h n of x, now this is a vector space. So that means as a vector space, it would be isomorphic to R to some power. You know, this is a lot simpler than homology, because homology, you're getting an abelian group. And abelian groups, they're not too hard, but they're a little bit more complicated. You can have a certain number of z factors, and then you have integers mod n with different modding of different n's. So it could be a bit more complicated, but cohomology is a lot simpler. It's a vector space, which is simpler than a group, abelian group, and if it's finite dimensional, it's just R to whatever dimension that is. So that's what it's going to be. And you actually had a homework problem, right? This was a homework problem that you had. If x has k components, so by components I mean path components, then the zeroth cohomology of x as a vector space is isomorphic to R to the k. Actually, to be fair, the problem on the homework would have to do with an Euclidean open set, but you can generalize the reasoning to actually any smooth manifold. So if you carefully look at the homework problem, you assumed that x, so on the homework you assumed that x was equal to u, where u was some kind of Euclidean open set in some dimension. It did not really matter what the dimension was. And you calculated that the zeroth homology, I'm sorry, the zeroth cohomology was this. But you can generalize it to a smooth manifold as well without that much effort. It's just a little bit harder because you have to recall a bit more definitions. But it's kind of interesting that you look at this result, and then you look, well, I realized I took it down, but the other one was with, when you're using a homology, you're getting z to the k. So that's kind of interesting. It's like, on a very simplistic level, you're doing the same thing, but instead of using z, you're using r, right? I mean, like, so naively, you're doing the same thing, but instead of z, you use r. Okay, that's a fairly ridiculous way to put it, but as you will see, that is often the case how it works out. We're gonna make this more rigorous, but that's what it works out. And it's kind of interesting the way you approach it, that this one uses a calculus, whereas this one uses topology. It's like you arrive at the same conclusion, but you're using two different methods. Because if you've done the homework problem, basically the way you figure this out, it comes down to the recognition So when you're working with the zero forms, you're essentially asking so you go back to zero forms, okay? So you would go back to zero forms, and you're asking which of these zero forms become zero, right? That would be the kernel. I'm sorry. Right, that's right. That would be the kernel, right? What's the kernel? The image is not anything because it's just the image of zero. So it really comes down to the kernel. What's the kernel of that? So you're asking what smooth functions have derivative equal to zero? That's basically what you're asking. So when is the derivative equal to zero? So the derivative is equal to zero when the function is constant? Not quite. When the function is locally constant. So it's constant on each of its components. So you end up reaching the same result, but you're using calculus. And when you're doing homology, you're reaching the same result, but you're using topology, you're using path connectedness. The idea there was that if your space breaks apart into many different components, if you have a point here, and then you have a point in the same component, then it is possible to connect them by a one chain, and then the difference of those 2 points is the boundary of the one chain. However, if they end up in 2 different components, then you cannot connect them by a chain. So you end up reaching the same result, but there you're using topology. So it's kind of interesting that you're almost doing the same thing, but from a different point of view. Here you're thinking about topology, paths, and chains, and things like that. And here you're thinking about derivatives and how they vanish and things like that. So, and they lead to the same result in the end. So this is the definition of cohomology. Cohomology, this is going to be a vector space. In general, in many cases, especially the spaces that we care about, it's always going to be R to some power. We have to figure out what that power is. And we're going to discuss how to compute it. So the question that comes up, of course, is how to compute cohomology. Right? That's the first question that's going to come up. And so how about we first focus on that and look at some examples to address that question. Now, we can compute homology by using the Mayer-Vittorius sequence. For homology. And you will see that you can do something very similar for cohomology. So you assume that X is a union of 2 open sets. They actually do not need to be open sets, but let's not overcomplicate it. So X is a union of 2 open sets. Then we have an exact sequence which goes like this: Hn of X. Let me write it like this: Hn of U intersect V. You can map that to Hn of U plus Hn of V, and then you can map that to Hn of X. And then the trickiest one is the one that lowers the dimension. So then you lower the dimension, it goes Hn minus 1, and then you return back to the intersection, and then it keeps on going. A lot of the times, we do not even need to know how these maps are defined. Sometimes the exactness of the sequence is sufficient to compute the homology without any additional work. And then sometimes we actually have to think about what the maps do. It just depends on how difficult the computation is. But for the sake of completeness, let's describe what these maps do. So this map, let's say you pick a cycle. C is a cycle. Now technically it really is a homology class of the cycle, but you pick a cycle, right? This is just a representative for that class. An n cycle, so that means its boundary is 0. It's contained. Technically, when we say the cycle is contained, we mean that all of a cycle is a formal sum of mappings, and we mean that the image of the mappings are contained in the intersection. So you're going to map it diagonally. So you're just going to map it to C comma C. Now you have to understand that this is a cycle in the homology of U. So that means that it is conceivable that C is non-zero, is a non-zero cycle. I mean, homologically it's non-zero in the intersection, but in this larger space, it does become 0. So it is possible that this one becomes 0, but this one stays non-zero. So you just have to understand, when I write C comma C, I'm just choosing a representative. The actual homology class could become 0, for instance. So you map it diagonally. Now, what's the map that goes here? So the map that goes here will take a homology class in this one, let's say C1, and a homology class here, C2. And because these are contained in U and V themselves are sitting in X, you can view these as cycles inside X. And then you take these two cycles and you subtract them. This is formal subtraction, because the homology groups is just the group generated by all of those cycles. So you just take formal sums of those cycles. And we're subtracting them. And you should notice that this is, in a way, arbitrary, because you could say, why do we subtract C2 from C1? Why not, let's say, do it the other way around? You could do it the other way around. You just have to make a choice. So let's say this is the choice that you make. Now, this is the one that is hard. This is the one that's hard to describe. So this is, so here's the way that it works. So kind of write it over here. So we pick a cycle, an end cycle in X. Of course, a representative for a cycle, for an end cycle in X. It is possible to write C as a sum. And maybe I want to be a little bit careful here. I should maybe say C is equivalent to, not equal to, but equivalent to, as A plus B, where A is a chain in U and B is a chain in V. So it's best to show this in a picture. Let's say this potato-shaped region represents U, and here's another potato-shaped region that represents V. And you have a cycle, let's say a one-dimensional cycle in X. So maybe it does something like this. What we are saying is you can split this cycle into two pieces. So this piece you call A, and the other piece you call B. You split it into two pieces. Now, technically, you cannot say that C is equal to A plus B. That would not be correct, because when we're dealing with chains, they are formal sums. And I understand that A and B together give you C, but when you're dealing with these chains, there are no equivalences. These are just formal lists of things that you have. This is a list of two separate things, whereas C is just one single thing. So formally, these are actually different. This would be incorrect to say. However, on the level of homology, you can say that C is homologically equivalent to A plus B, that C is an end cycle, and the sum is a cycle, and these two cycles are now equivalent when you look at it on the level of homology. So you can decompose every cycle in such a way. This is what we call barycentric subdivision. Intuitively, it makes a lot of sense, but proving it rigorously takes a lot of work. This is the reason why it's important that U and V are open sets, because there's a little bit of separation between them, and then the idea is you can take your cycle and then you can cut it up into tiny little subcycles. I mean, it's basically like partitioning a path. You cut it up into small little subcycles so that the formal sum of the remaining smaller cycles, even though on the level of chains you will get something different, but on the level of homology you will get something that's the same. Okay, and now you have to be very, very careful over here. So warning, A and B individually might not be cycles, but A plus B together form a cycle. Okay, so as you can see in the picture here, A is like one side and B is the other side. These are not cycles themselves, but their formal sum will form a cycle. So this is now a cycle, and homologically it's equivalent with C. And the way you end up defining this map, so sometimes we call this map boundary. That's how we often call that map. You're going to take the one for A, and you're going to apply this one to A. So you're going to take C. You're going to represent it instead as A plus B, and whatever that is, you're going to apply the boundary only to A and not to B. Now you might find this somewhat confusing when you first see this. You might say, why? Now, first of all, as you can see in the picture, the endpoints of A and the endpoints of B, they're contained in the intersection. So the boundary of A will give you something in the intersection. Now, also, whenever you take the boundary of a chain, even if A itself, you see A itself does not, as it says over here, A and B individually might not be cycles. So A and B might not be cycles, but the moment you take their boundary, you lower the dimension and you automatically get a cycle, because the boundary of a chain always becomes a cycle. So you're going to end up getting a cycle. So now you have a cycle of one smaller dimension in the intersection. Now, what people might find this a bit concerning is, why do you apply it to the first one and not the second one? Well, you could apply it to the second one. So what you would do is, you have to understand that because C is homologically equivalent to A plus B, that would mean that the boundary of C would then be homologically equivalent to the boundary of A plus the boundary of B. But the boundary of C is going to be 0 because it's a cycle, and that would mean that the boundary of B is homologically equivalent to negative the boundary of A. So instead what you could do is, if you do not want to use the boundary of A, you could replace it by negative boundary of B. But then you might complain and you might say, well, why negative boundary of A? Why not just boundary of B? Why do you have to put a negative here? Well, the reason for this is it has to be done so it's consistent with, it has to be done in a way so it's consistent with this one. You see, this one is positive, this one is negative when you apply this map. This one has to be consistent with how this one is being done, because you're trying to get an exact sequence out of it. So that's why you have to do it that way in order to preserve the exactness of the sequence. So this is the trickiest one. And in most of our calculations that we've done, we never actually had to work that one out, fortunately. But this is how the Meyer-Vittoris sequence works. And now we're going to get to the Meyer-Vittoris sequence for cohomology. But this one's going to be trickier because it will invoke new things that we have not seen before. Okay, so let's maybe we'll keep it here. Okay, this is the Meyer-Vittoris sequence for homology. Let's remove all of this. And one can prove in a very similar way that there is a Meyer-Vittoris sequence for cohomology. So this is Meyer-Vittoris sequence for cohomology. So here, X is a smooth manifold. You should notice that when we work with manifolds, and I've said this many times, we often never even mention the atlas. We kind of understand that it's there in the background, and we can invoke it if we need to, but we try not to. And when we make this extremely explicit, I will go back to the atlas again. But I want to write it without the atlas, kind of show you the way you want to think about it. And then kind of put in a lot more details into it, and then we can do a calculation. So Meyer-Vittoris sequence for cohomology. So what's going to happen here is X is a smooth manifold, and X is a union of two open sets. So here, U and V will actually have to be open sets, whereas in Meyer-Vittoris sequence, they do not have to be open sets. But here they will have to be open sets for the simple reason because an open subset of a smooth manifold is a smooth manifold itself. So you actually need it. You need it to be an open subset. Otherwise, you're leaving the category of smooth manifolds. So this is a smooth manifold. We have an exact sequence And this is going to be an exact sequence of vector spaces. These are real vector spaces, whereas this is an exact sequence of abelian groups. An exact sequence of vector spaces, and the arrows will just, it's exactly the same thing as before. So this is what we have. Now, the trickiest of these maps, so these are, by the way, linear maps, right? These are vector spaces, linear maps. The trickiest one of these, as you can imagine, it's the one that's going to be increasing the dimension, just like this is the trickiest one to explain. And you can call it D, perhaps, but I think people often just call it delta like this. Doesn't really matter what you call it. And this is what we're going to go through. Okay, so how do you go? So these ones are fairly easy to understand. These are like the ones that you typically think of just off the top of your head. Like, it's like you kind of think of the obvious mappings, and these are the ones that you use. This one's a bit trickier. So this is going to be the same thing. It's the obvious mappings here. Okay, so here's how you do it. We're going to, so I have to actually invoke an atlas. So we will have to invoke the atlas here to explain this. But basically, maybe I'm going to do it in a very sloppy way. I'm going to do it in a very sloppy way, and then I will make it more explicit. So in a very sloppy way, let's say omega is an n-form on X. Now, what that really means, when you go back to the definitions, is omega is a collection of Euclidean forms defined in each of the charts in a way that is coherent, right? But we just write omega. Omega just is a shorthand that represents that entire coherent family. The way you go from here to here, there's an obvious way you can go from here. If something is defined, if a function, you can think of a form as a generalization of a smooth function. A smooth function is just one single function, whereas a differential form, it's like a list of functions for each of the differentials. So how do you go, if you have a smooth function defined in X, how do you get a smooth function defined in U? You just restrict. So going from here to here, you would just restrict. You would just say it's omega restricted to U, omega restricted to V. Okay, and then how do you go from here to that one? Well, the way you would do it is, let's say you have, going from here to here, let's say you have omega 1 and you have omega 2. By the way, I should say that, I guess this is important, I should say this. When I write omega, omega is an n-form. But remember, if it's in the homology, it means its derivative must be 0. So do not forget that it's sort of like a cycle. So with a cycle, you would say it has 0 boundary, but here you would say it has 0 derivative, a 0 exterior derivative. So if it's an n-form, something in the kernel of the derivative operator. Okay, so it's sort of the role of a cycle. And of course, when we write the derivative of a form, what we really mean is you apply the derivative operator on each of the charts, and you get another new coherent family. But what does this mean? Yeah, we'll get back to that. And this, what would mean is that, let's say this is an n-form defined on U, whose derivative is 0, and this is an n-form defined on V, whose derivative is 0. How do you get an n-form on the intersection? Well, the way you would do it is you would take omega 1 restricted to U intersect V. You would take omega 2 restricted to U intersect V, and then you would subtract the 2. You would do subtraction here. It's kind of very similar to what you do over here. Here you take your two chains. You have a chain here. You have a cycle here. You have a cycle here. And the way you move to the next one is you subtract them. You make an arbitrary choice of which one is first, which one is second, but you're kind of doing the same thing. You're taking this form and that form. The forms are defined on U, so you can restrict the forms on this slightly smaller open set, and then you would subtract them. Okay? And then by subtracting them, you end up getting a form that is defined on the intersection, and this form will have zero derivative because when you apply the derivative operator to this, when you distribute it on each of the two pieces, the derivative of this one would be zero, and the derivative of that one would be zero. This has to do with the fact that omega 1 and omega 2 themselves are coming from cohomology. So by definition, their derivatives will be zero. Okay, so, and this is the one which is hard. This is the one that is hard to describe, and we'll get back to that. But the question for the time being is, what exactly do we even mean by restricting a form to a smaller open set? What do we mean by that? So if you want to, you can try pausing this video and see if you can take a guess. It's the first thing that comes to mind. If you can recall all of the definitions, it's the first thing that's going to come to mind. But here's the way you're going to do this. Maybe I'll give you a little bit of a hint. So let's say we have an atlas, phi lambda, mapping RK into X, be an atlas, a smooth atlas for our manifold X. Okay? So we have a collection of coordinates. And here we're going to assume that this is a k-dimensional. You know what? Maybe we do not even care. Maybe I'll just write it like this. Maybe we'll just write it as U subscript lambda. Well, you know what? How about we change this to a different letter? How about we call this O subscript lambda, where this is an open Euclidean set. Open Euclidean set. Or maybe we call it E subscript lambda. So where E subscript lambda is an open set in some Euclidean space, the dimension of which we truly do not care about. Like that. Okay, so let U be an open set in X. So without loss of generality, we can assume that U, maybe I'll add a little bit more. Yeah, let me add a little bit more. So phi lambda maps this Euclidean open set, E lambda, homeomorphically onto an open subset, let's call it X subscript lambda, of X itself. So X is a union of all of those open sets. Basically what we're saying is the charts completely exhaust and they cover X. So now, let's say we pick an open set, an open subset of X. We can assume, without loss of generality, we can assume that this open set is a union of a smaller collection of these. So to draw a picture for you, let's say this potato-shaped region represents X. And then you're covering it by these charts. So you have X1, and they overlap. You have X2. Maybe this is, yeah, maybe this is like X1. Let me do this again. So maybe this one is X1, Maybe this is x2, and then maybe this is like x3 or something. The charts will overlap. I mean, not necessarily any two of them, but in general, they will overlap. And we're saying, assume that this open set that you're choosing, now you could, of course, choose an open set that is like this is you, like over here, but that's not what we're assuming. We're assuming that the open set that you're picking itself, so X is a union of all of these, and we're assuming that the open set that you're picking can be expressed as a smaller collection of these. So maybe it's the union of x1 and x2. So our open set would therefore look like this. It would be all of this then. So that would be U. So we're assuming that U is a union of a smaller collection. Let's call it lambda 0. There's a smaller collection for some sub-collection. Now, if this bothers you, why are you allowed to assume this? It just has to do with a very simple fact that you can enlarge your atlas. If you have an atlas and it's not big enough, it does not have enough open sets, you can just keep on adding more open sets to that. You just keep on making the atlas larger and larger until it starts to include the open set that you want. You actually had that question on the homework. It's true that you're changing the atlas, you are getting a new atlas, but the topology never changes. And if you're interested in the topology, the atlas that you're using is completely irrelevant. So you just make sure the atlas is large enough that that open set is in there, right? I mean, it's not a big deal. It's going back all the way to what I said at the very beginning. When you're working with smooth manifolds, you try to never even bother mentioning the atlas. So this notation is very simplified. It's just omega. Now, if you want to really write out what that means, you have to go back to the atlas, okay? And if you really want to write out what that means, you got to go back to the atlas. And here I'm showing you how you actually do it. But we often keep the notation simpler by not bothering to go back to the atlas. But anyway, so then how do we restrict the form? So for a form, omega, so if you have an n form on X, we can define the restriction of the form to that open set, and that will give you an n form on U. How do you do it? Well, at this point, what you can do is you can pause the video and see if you can figure out. It's the first thing that comes to mind. So the way you do it is you have to go back to the definitions. What would be an n form on X? Well, this would be, if you want to be very formal about it, this would be a collection of Euclidean forms where each omega lambda is a form, an n form, on E lambda, on that Euclidean open set. And furthermore, the collection is coherent. How do you then get a form on U? Well, U itself is a smooth manifold where you use the exact same atlas, but you just use a smaller sub-collection, right? That's all you do. It's the exact same atlas, but it's just running, the index is running over a smaller sub-collection of lambdas. So here lambda is in this indexing set, and omega restricted to U would just be, it's the exact same collection, but it's just being restricted to the smaller sub-collection. And everything remains the same. And it will still be coherent because it's just a smaller family, right? I mean, the larger family is coherent. So this will be coherent. That's exactly how you do it. It's the first thing that comes to mind. And that's how you end up getting an n form on that open set. Okay, so that's how it works. And that's how you restrict. And this is the Meyer-Vitora sequence for cohomology. Okay, so this is all nice, but what about this difficult part? Can we explain what that map is? So that is the one we're going to talk about. And it would be helpful to remove everything from the screen and to start all over again. It's going to be kind of tricky to do. But before we do anything, I think actually what I should first do is I should do an example with you of where we compute this, a computation where we use the Meyer-Vittori sequence for cohomology. And in that computation, we do not even need to know how this map is defined. It's just not going to matter for us. So I think that would be helpful. So before we confuse ourselves by defining this delta map, how about we first do a computation for, let's say, a circle, right? One of the easiest spaces for the cohomology of a circle through the Meyer-Vittori sequence for cohomology. We see how it works. And then after we understand, we can kind of go back and think about this all over again. Let us do an example where we compute the cohomology of the circle. I'm going to compute the, let's say, the first dimensional homology, the cohomology of the circle. Now, before we do the computation, let's try to take a guess about what we think the answer is. We know that the homology of the circle, that's isomorphic to the integers. And so the cohomology of the circle would be the vector space that's isomorphic to R. So it's a one-dimensional vector space. This is like the easy way to get it if you know what the homology is. But that's not very satisfying because we want to see the definitions carried out very carefully, even though there's an easy way to do it, and use the Meyer-Vittori sequence for cohomology. And of course, the question here is, how do we even justify this fact? How do we justify that the way you get cohomology, the easy way, if you happen to know what the homology is? How do you do that by just replacing the integers by the real numbers? That also requires justification. But it happens to be true, and we'll talk about that more carefully in a different lecture. But for now, we want to justify this more closely by using definitions and by also using the Meyer-Vittori sequence. So here's the way we're going to do this problem. We're first going to begin with an atlas. S1 has the atlas. And this is the atlas that we've used before, an atlas that consists of two charts. One of them we call F plus, the other one we call F minus. And F plus, this is the function we usually denoted by an S coordinate. It maps the open unit interval, and it maps it to by e to the 2 pi is. And F negative, this is the t chart in the t variable, and this is the one that does this. Okay, and the charts here is the image of this one. It's going to give you that part of the circle, and the image of that chart will give you that part, this open subset of the circle. And then you can see that these two, they end up covering the circle. So this is what we've been using before. And we're going to compute the cohomology of the circle using this atlas. It actually does not make a difference what kind of atlas you use. You can also do this using stereographic projection or any other coordinate systems that you want, because when you're working with manifolds, when you're doing topology, you do not really care about the atlas. The topology remains the same. The atlas is just basically coordinate systems you have to pick locally to do the calculations in, but the actual topological space remains the same. So now I should say that before I go on any further, that if in many books, when they do this calculation, they might not even bother to even tell you what the atlas is. It's just a question of how many details do you want to put into your calculation? Like, how much do you want to write out? Here we're going to be writing a lot more because we want to practice the definitions and all of that. But a lot of the times, if you're looking up this calculation in a book or some other calculation, it will be a lot shorter, not necessarily because they're using some kind of theorems in secret, but it's just because they're not writing out every detail. So here, to do this we're going to compute this using Mayer-Vitoris. And U is going to be this open set, and V is going to be this open set. So basically, U and V are going to be the charts themselves, right? The image of these charts on the circle. So you notice that we're choosing open sets that are already coming from the atlas. However, if you look at their intersection, so observe that if you look at the intersection of U and V, you're going to be getting this. It's these two components of the circle. This is a path disconnected space. And you realize that this open set cannot be obtained by the charts, right? It's not a union of these two. It's something smaller. So what you can do is you can modify your atlas by adding to it more open sets. Often we never even bother to do that because it's self-understood. But if you want to be very careful, you can enlarge A. I'm going to call it A again. And you're going to have F plus, you're going to have F minus, and then you throw in a new chart. You can call that chart G. Or maybe how about we call it F? Let's just call it F. Where F, and this is going to be a function defined. So these were defined on the open unit intervals. This one was defined from 0 to 1. This one was defined on 0 to 1. And this one's going to be defined from 0 to 1/2. Union 1/2 to 1. By the way, there's millions of ways to do that. It does not matter how you do it, as long as you just include more open sets into your atlas. This is just one way to do it. If you're thinking to yourself, why not have a chart that's defined on that interval and another chart that's defined on that interval, you can, of course, do that. It's not a big deal. There's so many ways to do it. And this one, this function, I'm actually going to use the exact same letter that I use for the positive chart. So I'm going to use the same letter again. I'm going to use the letter S. Why am I going to use the same letter? Well, because I'm going to use the exact same function, the exact same mapping function. 2 pi I S. So then there is no ambiguity, because if I tell you the S coordinate, there is no ambiguity whether I'm referring to this chart or to that chart, because it's the exact same function, just restricted on the smaller set. So that's why there's no ambiguity which one you're using. And then by doing this, the intersection of U and V, as you can see, is now the image of this chart, right? The image of this one, it's the image of U, I'm sorry, the image of F plus, which is U, and then you're leaving out what happens at 1/2. So you're leaving out that point, and then you're getting that one. And if you're bothered by this, and then you're saying, well, what about, well, why are we leaving out F minus? Well, if you want to, you could include in F minus as a 4th additional chart. It really does not matter. It's not going to do anything for you in the end. The whole point that I'm trying to illustrate is, the moment you have an atlas, if you have an open set of your manifold that is not part of the open sets coming from the atlas, that is no problem whatsoever. You can just throw in more open sets into your atlas, so that the intersection is now, you can get the intersection as a chart or a union of charts from the ones that you already have in the atlas. A lot of the times, people would not even bother to do that, because some people would say it's self-explanatory that this is what we're doing. But because we're learning this for our first time, we're being super careful with the procedure. Okay, so we have an atlas, we've enlarged it, and now we can compute cohomology. So now we go ahead and we apply the Mayer-Vitoris sequence. So we would have that the first cohomology of the circle, it's going to go to the cohomology of U plus the first cohomology of V. And then here you would have H0 of the intersection, H0 of U plus H0 of V, and we would have H0 of S1, and here we would have 0. So this is going to be the relevant part of the Mayer-Vitorna sequence that we're going to be using. Okay? Now, we're going to compute this without any reference to topology, because we're going to try to do this in a self-contained way. So for instance, this one right over here, you would say that this is 0 because U, well, if you look at U, what's U? So this is U over here. This is a contractible space. And the first homology of a contractible space is 0. So you would therefore guess that the cohomology of U should be the 0 vector space. And you would be correct. But I do not want to do that because we're not doing it directly by definition. I want to do it specifically directly by definition for learning purposes. So you're right, like this would be 0, that's going to be 0, but we want to actually see that, how it follows from the definitions. And this will actually illustrate, like as we're doing this computation, you will see that cohomology is easy. This is easier to actually compute. Like you can appeal directly to the definitions here without doing much more, without doing extra work. With homology, we had to actually rely on various theorems to get some results. Like when we did this using homology, with homology, so when we talked about the first homology of that arc, we used the theorem that homology is a homotopy invariant, and that entire arc can be homotoped down to a single point, and then we use the well-known fact about the homology of a single point. So we had to actually use theorems to help us do the calculations, but as you will see, as we compute out the sequence, we do not have to use any theorems whatsoever. That it's because cohomology is simpler, so we do not have to use any additional tools to figure this out. But anyway, how would we complete the calculation? So let's talk about the 0 homology of the circle. Now this is going to be R, right, isomorphic to R as a vector space, but how do we justify this? So here's the way we're going to justify this. In order to do this, we have to understand what this represents. We have to pick a 0 form, omega, a 0 form. Now a 0 form is just a smooth function. So a 0 form, how would it look like? It would be a collection of forms, and by 0 forms we just mean smooth functions in each of the charts. Now I did not say this earlier, but the reason why this is a smooth atlas is because the change of coordinates between these two is a smooth function. We saw that before. And the change of coordinates between f plus and f, that would just be the identity map, because this is the same exact function, just restricted to the smaller set. The change of coordinates between f minus and f would be exactly the same thing as the change of coordinates between f plus and f minus, because f is just coming from f plus. So even though you're enlarging the atlas, the change of coordinate functions really remain the same. And very often, we never even bother to write omega, what omega is doing in this chart, because it's the same thing it's doing in the positive chart, just restricted to a smaller open domain. So if you're picking a 0 form on the circle, that by definition would mean you have a 0 form on this. So it would be a 0 form on this interval, and you would have a 0 form on that interval, right? You technically have 3 charts, but this is sort of redundant because it's going to be the exact same functions that you're using over here. So you just have to say what it does here and what it does over here. So it really is going to be a collection of 2 smooth functions. You're going to have a function, let's say, a of s and b of t. That's what it's going to be. A of s, this is a smooth function defined on this one, and b of t is going to be a smooth function defined on that one. So a 0 form is just a collection of 2 smooth functions, each defined on these 2. And this has to be a coherent collection. That the change of coordinates from this one to that one will be the same. Now, if you recall, the change of coordinates is the way you get the s coordinate is you take the t coordinate and you add to it either plus or minus 1/2, depending on whether the value of t is between 0 and 1/2 or whether it's 1/2 and 1. So that's the relationship between s and t. So this kind of relationship will have to be satisfied between these two functions. So it will be a collection of two smooth functions. A of s is defined on this one. B of t is defined on that interval. And the function, these two functions are smooth functions in the Euclidean sense, and they will satisfy the property that if you take s and you replace it by that, it will be equal to the other one. So that is what omega represents. Now, it has to be in the cohomology. So it means that d omega is equal to 0. What do we mean by d omega? The way you do calculations with forms is that these are calculations in each of the charts. So you're going to take the exterior derivative of a of s, and then you're going to take the exterior derivative of b of t. So when you take the exterior derivative of a of s, you're going to get a prime of s ds, and here you're going to get b prime of t dt. And we're saying that it should be equal to 0. So when we're saying the exterior derivative is equal to 0, we're saying that in every one of the charts, this has to be 0. So this one has to be equal to 0, and this one has to be equal to 0. But what does that mean? So this is just a formal symbolic. It does not mean anything, but you have a prime of s. So you have a function whose derivative is 0. That means a has to be a constant function, and b has to be a constant function. So that means this is a constant, and this is a constant. They're both constant functions. But because of coherence, they have to be the same. They have to be the same function, because whatever constant this is, when you change coordinates, it will have to be consistent with this one. So there has to be the same constant. So really, in the end, it's just a real number. And because of this, we can therefore say that this thing is isomorphic to the real number, right? Because you're just picking a real constant. Whatever real constant you pick in the s coordinate, you have to pick the same constant in the t coordinate because of coherence. So this is the careful explanation for why the zero cohomology has to be isomorphic to the real numbers. Okay, so to say this again, because when you pick a zero form, since it's in the cohomology, by definition, it means the form has to be in the kernel. It's something with zero derivative. So its exterior derivative has to be 0, and then you do calculations on each of the charts, and then you see why isomorphic to the reals. So that's why this is just R. Now, what happens over here? Well, this is going to be the exact same explanation. So I'm going to remove this, and now we're going to focus on this one. What happens if we pick a form on U? Well, what would this mean? So U, the way you would do this is U is a subset, is an open subset of the circle. And you would express U using a subcollection. You need a smaller collection of charts in the atlas. So to get U, you would have to use F plus, and you would have to use F. F is really redundant because it's just coming from F plus. So you do not even bother to even write it out. But you can get U by using this chart. And then because, well, technically you have two charts, but this one's redundant, so we just focus on the F plus chart. On the F plus chart, a zero form would then be a smooth function on that interval whose derivative is 0. So it has to be constant again. It would have to be constant throughout that interval. So for the same reason, what that would mean is this would just be isomorphic to the real line. This would be isomorphic to the real line. And then this would be a sum, right? A direct sum of two copies of the real line. You have two independent constants that you can pick on each of these two. Okay, so we have that. And then we have to say something about this. I'm going to leave this up to you to think about, but this is going to be also, so this is going to be r squared. This is, of course, r squared also. This is going to be r squared for the simple reason because when you look at the intersection, you can find the intersection in the atlas, but you would have to use that chart. And then you're saying the derivative, you have a function whose derivative is 0. Well, if the function has 0 derivative, it means the function has to be constant on each component. So it would have to be constant, because this is disconnected. It would have to be some constant value on this interval and a possibly different constant on the other interval. So because of this, you can pick 2 independent constants on each of these 2. So that's why H0 would therefore be isomorphic to R squared. Okay, this is the one we're trying to find. But what can we say about this one? So why is this one 0 and why is that one 0? So let's explain that. So let's say we pick omega in H1U. So by definition, that would mean that omega is a one form. It's a one form in this coordinate and a one form in that coordinate. Again, you do not even bother to say what it's doing in this coordinate because this is just a repeated version of that. So omega is a one form in this coordinate. So a one form by definition, because this coordinate is a Euclidean open set of one dimension, there's only one differential to use. So it's going to be some function. It's going to be some function, let's say a of s ds. And then it would also be some one form in the other chart. So it'll be some other function, some other smooth function, dt. And these are going to be coherent, as before, that as you switch coordinates from here to here, that the 2 forms will be compatible with each other. Now, because this is a one form, well, if it's in the cohomology, it must mean that the derivative of omega is 0. So what conditions do we have to put here? Well, there's no conditions that we can put here, because if you were to take the derivative of omega, that would be equal to, so you would take the exterior derivative of a of s, which would be a prime of s ds, and then you would wedge it with the symbolic that you're already using. But because these 2 symbolics repeat, that will just give you 0. So you can see there's actually no conditions that you have to put on these functions. The exterior derivative will automatically be equal to 0. Okay, so, but then you could say, but if there's no conditions, why do we say it's equal to 0? Well, you have to understand that when we're working with cohomology, in a very similar way, just like homology, we're technically working with equivalence classes. And we are claiming that this coherent family of one forms is the derivative, is the exterior derivative of a 0 form. It's exactly what you do when you're working with homology, that when you say that something is homologically trivial, it means there's something of one higher dimension whose boundary gives you the cycle. Here, it just goes in the other direction. So when you're saying that this one form is cohomologically trivial, you are saying that you can find a form of a previous dimension, in other words, a 0 form, whose exterior derivative will give you exactly this. So can you do that? Yes. And it just has to do with the simple fact that antiderivatives exist. So what you would have to do is, you would have to pick an antiderivative. You have to find an antiderivative for that function. In other words, capital A of s is a function whose derivative will give you this. So then if you differentiate this one, if you differentiate it, you would get exactly that. And if you differentiate the other one, you will get exactly this. Okay? Now you might say, how do you know that this is a coherent family? Well, the reason for this is because if you find an antiderivative, you can always choose it up to a constant. So if this function, yeah, so basically you take, we know that this function and that function, they're coherent with respect to changes of coordinates. So we know that. So you just calculate an antiderivative for this one, and then you calculate an antiderivative for that one. And if these functions are not compatible. Well, if they're not compatible, then all it means they're not compatible up to a constant, because they both differentiate into the same thing, right? Into something that's coherent. They differentiate into something that becomes coherent. So because they differentiate into something that becomes coherent, it means whatever these two functions are, they would be coherent up to a constant, right? That's up to a constant. So if this is not coherent, then you can just fix your choice by adding in an appropriate constant that you're off by, so that this collection of functions becomes coherent. And then this will be a smooth family of zero forms, right? Defined. So this one's defined on that one's defined on the other one, that are coherent because the original A of S and B of T are coherent, and they differentiate into the required forms. So what we see is that this one form is the exterior derivative of a zero form. Right? All we're doing basically is we're just using the fact that if you have a function of a single variable defined on an open interval, you can always find an antiderivative function. Right? That's really all what we're doing. And so the conclusion is that every one form is the exterior derivative of a zero form. So everything in anything, yeah, so anything, any one form comes from a derivative of a zero form. In particular, the cohomology is trivial, right? So this is and this is trivial for the same reason. So this one ends up being the zero. This one ends up being the zero vector space. So this is the sequence that we have. So maybe we can remove all of this. And now we can discuss what these maps do. So let's give these maps name. Let's call this map A, B, C, D. This is just the zero map. You can give it a name if you want to. I do not think we need a name for it. So the map that goes from here to here, it's going to take a real constant, and it will just assign it to the same real constant. This is just a diagonal map. Right? This is the way the map is defined in the Meyer-Vitorta sequence, the diagonal map. Now the map that goes from this direct sum, so this is r squared, to r squared, that's not the identity. This is the one that's given by a difference. So this is the one where you're going to take two independent constants, r1 and r2. So r1 is a constant chosen for the constant function that you're setting on u. This is the constant function you're setting on v. And then you can restrict this constant function to a constant function on the intersection, and restrict this constant function to a constant function on that intersection, and then you end up subtracting them. So the way that this map is defined is that this is going to be really be r1 minus r2, r1 minus r2. If you're confused by this, let me maybe draw a picture for you to make it a little bit easier. That this is the circle, and you're breaking it up into two components, like this. So the reason why this is r squared is because you're making a choice for the constant, for your smooth function. So this is a function with zero derivative. So it has to be constant on that cap and constant on the lower cap. And then you're making a choice over here. So you have to make two independent choices for the upper piece and for the lower piece. Now the function that goes from this direct sum over to here, it's given by restriction. You're taking a function, a constant function, that's defined on u. So here you only have a single choice, and this is v. So you only have a single choice you can assign, a single constant you can assign on u, and there's a single constant you can assign on v. You're taking these two constant functions, you restrict them to the smaller open set, and then you subtract those two constant functions. So whatever constant you are assigning on this one, and whatever constant you're assigning to that one, they could be two independent constants, and then you subtract them, right? But so you're subtracting the same constants, but the zero cohomology of this open set consists of two independent choices on the two caps. So by subtracting them, you're getting the same exact choice on each of the two caps. So you get the difference in the upper cap, and you get the same difference in the lower cap. So because of this, the mapping from R squared to R squared is the map that sends this pair to the difference. Okay, so, and maybe, yeah, then from here, maybe to make it even easier, this is 0, this is, well, this is going to be the mystery. This is the mystery vector space. This is the one we're trying to compute. This is the map that we're calling A. This is R squared. This is the map that we're calling B. This is R squared, and this is given by matrix multiplication. It's a linear map, and matrix multiplication here is going to be R1 goes to R1 minus R2. So it's going to be 1 minus 1 and then 1 minus 1. Matrix multiplication given like this, because it's the same thing repeated. And this is just R, and this is 0. So we call this C, we call that D. And this is going to be R to some dimension. Let's call it RD, where D is the mystery, right? This is the one we want to figure out. Is it 0? Is it 1? Is it 2? It will have to be a finite number, as you will see, because of the rank nullity theorem. But now we get to use the rank nullity theorem. We can say that D is equal to the rank of A plus the nullity of A. The rank of A is 0, because this is just the 0 map, plus the nullity of A. What's the nullity of A? Well, the nullity of A, by the exact sequence, that would be equal to the rank of B. Right? The kernel would be equal to the image, the rank of B. Now, how do you find the rank of B? But the rank of B plus the kernel of B, by the rank nullity theorem, that would be equal to 2. Because that's the dimension of this vector space. Okay, so now we have to find the kernel of B, right? So the kernel of B, I'm sorry, I should have said the nullity of B. Nullity is a number, whereas kernel is a subspace. We know that the nullity of B from exactness would be equal to the rank of C. And the rank of C is the rank of this matrix. And if you row reduce, you will get 1, negative 1, 0, 0. So you have an extra pair of rows unnecessary. You have one independent pair of rows. So the rank is going to be 1, right? So basic linear algebra will show that the rank is equal to 1. So in other words, C is not an isomorphism. Rather, C maps R2 to a one-dimensional subspace of R2. So that's why the rank is equal to 1. So this would mean that this is 1. It would mean that nullity is 1. So since rank is 1, it will mean nullity of A is 1. And in the end, it means that therefore D is equal to 1. And there we go. We completed the calculation. And what I want you to appreciate about this calculation is, so let us appreciate the fact that we were able to do this entire calculation directly from definitions, right? We did not have to use any extra theorems, which is not the case for homology. With homology, we actually had to develop many different theorems that allow us to simplify the calculations to get a result. I guess you could say we are taking advantage of the Meyer-Vitorta sequence, and that is true. But even when we do homological calculations of the circle, we have to use certain theorems that are not easy to prove. Namely, the one that we used a lot was that if you could homotope an arc to a point, then the first homology of that's going to be trivial. So it's not something that directly followed by definitions, but we're able to do this because cohomology, as you can see, is actually simpler than homology. And the other thing that I wanted to finish on with this example, so to finish with this example, Since the first cohomology of the circle is isomorphic to the real line, it means there is a one form on the circle which generates cohomology, right? Which generates the vector space. What is it? What is that one form? Well, actually, there's an infinite number of answers you can give, because the moment you find the generator, any non-zero scalar multiple of that generator will also be a generator. But to do it for you concretely, so recall that we found this form. We found this one form called d theta on the circle. And as we remarked, this notation is a little bit abusive because the angle function theta is technically not defined globally on the circle. But the reason why we write it like that, because the idea is that the local representations of the angle function, the moment you differentiate them, they give you the same consistent family of one forms on the whole circle. So that's why we kind of just call it d theta from the beginning. Okay, and we claim that d theta generates. So what we basically claim to say is that d theta, maybe I should say the homology class of d theta, generates the vector space for S1. So to do this, it is sufficient to show that this d theta class is not the zero vector. This should be simple, that any one-dimensional space, let me say this again, in any one-dimensional space, if V is a one-dimensional space, and let's say lowercase v is a vector and V is not the zero vector, then V generates the entire vector space, because it's just a single dimensional space, right? A single vector, as long as it's a non-zero vector, will generate for you the space. So we have to show that this is not the zero vector. More precisely, so precisely, this means that d theta is not equal to the exterior derivative of a zero form. Remember, to be zero in cohomology means it is the derivative of the previous form, of a lower dimensional form. Now, the reason why this looks absolutely funny is because the notation looks like that the form is d of theta, but the problem is theta is not a zero form. It's not consistently defined in every single chart. So how do you know that it's not possible to find a consistently defined zero form on the entirety of the whole circle that will end up giving you d theta? So here's the way that you know it. So maybe for simplicity, let's just call this thing omega to avoid confusing ourselves. So we claim that omega is not equal to d, let's say, I know we used the f before, but let's use f again. It's not equal to df for some smooth function on the circle. So how do we know that? So here's what we know. Let C be the one chain, and I'm just going to draw a picture for this one chain. This is the one chain this is the calculation we've done before. It starts at the top of the circle, and it goes like this. It doesn't really matter how you do it, but this is the calculation that we've done before. We saw that if you take the integral of omega over that chain, so this was basically what we were saying before, integrating d theta over the chain. This is the calculation we've done before, and we saw that when you go around the circle, when you integrate this form, it gives you 2 pi, right? This is what we got before. It's equal to 2 pi. Now, it's not the fact that it's equal to 2 pi that we really care about. It's the fact that it's a non-zero number. Now, if, for the sake of contradiction, so if omega was the derivative of a zero form of a smooth function, then, and now we're going to use Stokes' theorem. Then by Stokes' theorem, the integral of c of omega would be integral of c of df, but by Stokes' theorem, that would be the integral of f of the boundary of c, integrating a function over a zero chain. A zero chain is just a set of points, so we're integrating a function over a set of points. We're just evaluating a function over a set of points. But this is an empty set of points because C is it's a cycle. It's a cycle. So we're integrating this over, we're adding it over an empty set. So that's just equal to 0. So we have a problem. If omega was a derivative of a globally defined smooth function, then the integral over this one chain should vanish and give us 0. But at the same time, we've done a previous calculation that showed that the integral is equal to 2 pi. The answers, these two are contradicting each other, and the contradiction arises from the observation that this form cannot be the derivative of a smooth function. So because of this, the form that we have constructed, it is non-zero in a cohomological sense. And because of that, it actually generates this space, right? It will generate, this will be a generator for that vector space. So that's what we see. So I forgot to say this, but in the calculation that we just did, it was not required to analyze the delta map. So what's the delta map? So we had this map. So we were going from S1. We had this going to somewhere. This was going somewhere. And, oh yeah, this was the map that went from H0 of U intersect V, right? So when we were using the Meyer-Vitora sequence, there was a map going from 0 dimensions to 1 dimensions, and that map is typically called delta. That's the map that increases the dimension number. And we did remark that this is a map that is hard to describe. And as you noticed in the calculation, it was not even necessary to determine what it was, because the exactness of the sequence was sufficient for us to do it. But sometimes you might need to analyze what it is. So now what we're going to do is we're going to describe how this delta map is being defined. And it would be helpful to start with 0 dimensions first. Before it's just easier to describe what it does, and then it's the same idea for higher dimensions. As you will see, it's very similar to barycentric coordinates. Well, I should say barycentric subdivision that we had for the lowering of dimension map when we're talking about homology. So now that's going to be our next topic. How do we define the linear map that takes us from nth dimensional cohomology of the intersection to n+1 cohomology of the space? So X is your manifold, and it's been written as a union of 2 open sets which happen to intersect, and this is their intersection. And in the Meyer-Vitora sequence, we have this linear map between these 2 vector spaces that we call delta. So that's what we're going to be talking about, and it would be helpful to start in dimension 0. So to define how you go from the intersection to the union. So this is the union because that's what X is. And this will be based on the following fact from analysis. So this is really, you can say this is a fact from analysis. We're not going to prove this. It's a technical proof. And most courses, they never bother to prove it because it just comes up in a very unusual way in the course, like you often use it when you work with manifolds, but you have to then leave the subject of topology and switch over to analysis. And when you're taking analysis, you might not need to use this as much. So it's like one of those things that is often not proven in any course that you take. So I'm just going to tell you what it is. It says that let X be a union of two open sets, U and V, where X is a manifold. We can find smooth functions. Let's call these functions, I'm going to call this alpha U. This is a smooth function defined on X. It might be a little bit confusing because I'm writing subscript U, but you'll see what the subscript refers to. It's a smooth function defined globally on X. And another smooth function that's defined globally on X also, with the support of alpha U being completely contained in U, and the support of alpha V being completely contained in V. Now, I should probably remind you what the support is. So if alpha is a real valued function, let's say it's smooth. It does not have to be smooth, but you have a real valued function on a manifold. The support of your function, that's the relevant part of the function. The relevant part of the function is the non-zero part of the function. So when you're doing integration, that's the part that you really care about. This will be the points where the function is non-zero, not equal to 0. And we often, in the definition, we also take the topological closure of that set in X. So that would mean including up to the boundary. So it's the place where the function is not equal to 0, and then you also include where it is equal to 0 as well. So like right at that boundary where it transitions from non-zero to being 0. So that's what you call the support of the function. And so here, alpha U and alpha V, they're globally defined functions on your manifold, but their supports are contained in each of these two sets, and alpha U plus alpha V, it adds up to the unity function. This is called the unity function. It's the function that's identically equal to 1 throughout the entire manifold. And this is called, if you've never seen this before, this is called partitions of unity. That's what this is called. As you can see, this has a lot to do more with analysis, really. If you want to see a picture for what we're talking about, here's a very simple picture. Imagine that X represents the real line, and U and V are open intervals. So U is an open interval, and V is an open interval. And what we're saying is, I should say, of course, well, I want to discuss what happens if they do not intersect. If they do not intersect, then what we've just said is completely trivial. So actually, maybe I should talk about that with you. So let's say we have U and V do not intersect. So U and V do not intersect. And you want to find a function. You want a function that adds up to 1. So here's one way you can do it. You can define alpha U. So in this case, X would not be the real line. It would be a union of two disjoint intervals. You can define alpha U by the formula that it's equal to 1 if X is in U and 0 if X is not in U. And you can define alpha V the other way. You can define it to be 1. You can define it to be 0 if X is in V. Well, actually, sorry about that. You define it the same way. If X is in V and 0 if X is not in V. So basically, the picture would be that alpha U is going to be equal to 1 on U, and then it would be equal to 0 on V. And the point is, this is a smooth function. It's a smooth function because these two conditions where you're, well, if you're not in U, then you're in V, right? I should say it like this, right? Your X is in V or X is in U, because our space X is the union of these two intervals. So if you're not in U, then you're in V, right? So this is the way you can write it. If X, maybe write it like this. So X is in V, X is in U, like that. That's just another way of rewriting it. And the reason why this is a smooth function, well, because when you jump from one interval to the other interval, they're separated. So you can, these are open sets. It's not like they're coming close to each other. And so you have two separate conditions. And these are smooth functions. They can be infinitely differentiated. So you have two smooth functions. The support of alpha u. So where is this function non-zero? It's non-zero on this entire interval u. And the support of alpha v, that would be v. So you can see that each one of them is contained in the support of one of these two open sets. And together, when you add them up, right, when you add them up together, they give you the unity function, right? You're partitioning unity. You're partitioning the unity function as this kind of a sum. Now, if the two intervals happen to overlap, then this is not going to work, because these conditions will contaminate each other. So then the situation is going to be a lot more complicated. But if the two intervals, so let's say this is u, and let's say this is v, and they happen to overlap, then how do you construct the function? Well, there's a way to do it, but it's kind of tricky. You basically make the function be equal to 1, and when you start entering the place, so this is like the place where they start to overlap, right? This is like the place where they begin to overlap. So basically what you do is you keep the function be equal to 1, and when you start entering that intersection interval, you sort of gradually start to go like this until it becomes 0, like that. And then the other one on u, you keep it equal to 1, and when you enter where the two intervals intersect, then you make it plateau, and then you make it go like this. And if you do it just right, you can see that if you're on this piece, this function is equal to 1, that function is equal to 0. If you're on this piece, this is equal to 0, that is equal to 1. And if you're somewhere intermediate, then you're smoothly transitioning between 1 and 0. So if you're over here, maybe this is 0.7, but maybe that is 0.3. So that's the way you would do it. So this is one of those situations in mathematics where we care a lot more about the fact that this exists rather than how to do this. So maybe we could say this: we care a lot more that this exists rather than the explicit formula. We do not care what the explicit formula is. We just care that it could be done. And if you look at the support of u, where's the function non-zero? Well, it would be all the way up to this. That's where the function is non-zero. So the support is contained in u, the support of this one is contained in v, so all of the conditions are satisfied. And now, if you're wondering how one would prove something like this, maybe you've seen things like this before in an advanced calculus class, where you have one of those functions that is, maybe you recall there's like this function, it's equal to e to the negative 1 over x if x is positive, and it's equal to 0 if x is non-negative. And then it's the function that is, when you draw it, the function is 0 over here, and then it kind of goes like this. And what makes this function very interesting is that it's a piecewise defined function, but you can verify that this is actually a smooth function. You can infinitely differentiate it. So you're starting getting the piece of what you want, and then you have to keep on manipulating this function to get it to look like this. But this is, of course, what you would do on the real line. When you start dealing with an open subset of the plane, more work is required. And then you do this for general Euclidean spaces, and then you put in a little bit more work, and then you generalize this to any manifold. So when you actually go through the whole procedure, it's fairly tedious. It's quite long. Actually, interestingly, the way you prove it for a manifold, you have to use the fact that the manifold is second countable at some point. You will write the manifold as a sequence of open sets, and then you kind of reapply the argument on each of those open sets in the sequence, and that way you sequentially build the existence of such functions. So you can look at it if you want to. It's one of those theorems in mathematics that is overly tedious to work it out. And at the end, the only thing you really care about is the fact that it could be done, right? And I think it's fairly believable, but if you want to be rigorous, you have to put in the detail and show that this exists. So if you're willing to accept this, then here's the way you would make this work. So here's the way you define this function. So how do you go from 0 cohomology on the intersection to 1 cohomology on the manifold itself? So let me remove this and we begin again. So this is construction of this map from the intersection to the union. Actually, what makes this interesting is, in some sense, so in a way, this is the cohomological version of barycentric subdivision. Barycentric subdivision is also a very technical result that we just drew some pictures for and we were convinced that it works, but we never really wrote out the details. And this is sort of the same thing. But actually, this one is easier. It's not as tedious as barycentric subdivision, but it kind of plays the same role. It plays the same role. You're kind of subdividing unity into such a partition. So here's how you do it. So you're going to pick something in here. So you're going to let omega be. So what is that? So i.e. omega is f, where f is a smooth function defined on the intersection. Okay? So a 0 form, a 0 form is a smooth function, and furthermore, d omega is equal to 0. So what does it mean for a function to have 0 derivative? It means that i.e. f is locally constant. So if the intersection happens to be connected, then f is just constant. But in general, it will have components, and then f will be constant on each of the components. So we start with a smooth function, and we want to use it to create a 1 form on the union. So how do we do this? So here's the way the process works. So let me maybe draw a picture. Let's say this represents u. This represents v. So what we're going to do is we're going to let alpha u, alpha v be smooth functions defined on the manifold with their sum adding up to unity. So this is a partition of unity. And the support of the first function is contained in u, and the support of the second function is contained in v. Okay, so we have this setup. This is where we're using partitions of unity. And now what we do next is we're going to take our function and we're going to write f. So we take our function over here, f. This is our 0 form. And we're going to just multiply in 1 in there. That does not change anything. But then we use partition of unity to break it apart into 2 pieces, alpha u plus alpha v. You break it apart, you partition it in this way, and then you multiply it in. So this would be equal to alpha uf plus alpha vf. And this is all defined on the intersection. You have to be careful because the function is only defined on the intersection. This is the unity function on x, but you can of course restrict it to the unity function. This relationship that alpha u plus alpha v is equal to 1, that is true on x, but it's certainly true on this smaller open set as well. And then you decompose it in such a way. And you look at this and you say, well, how does this help us? Well, here's what you realize. So you have to observe that alpha UF is defined on the intersection, right? You're just restricting this. This function is actually defined on X, but you're restricting it to the intersection. So that's defined in X. However, alpha UF can be extended to a smooth function on the entire manifold by 0. You just extended by 0. So in other words, alpha 0f evaluated at a point X, what is it equal to? It would be equal to alpha U F. So you would just do alpha U at times alpha UX times f of X if X is in U. I'm sorry, if X is in the intersection. And then you would just set it equal to 0 if X is not in the intersection. So that's what you're doing. So maybe this picture will help. So you have a function, right? You have a function over here. You have a point. If the point is in the intersection, then this function, the way you evaluate it at the point is this is a product of two functions. So you apply f, you get something. You apply f, you get something, and then you multiply it by alpha ux, right? You multiply it by whatever that function is. And this is a smooth function, and that is a smooth function, and then you get something out of it. Now, what if you have a point, and if you're outside the intersection, right? If you're not actually in the intersection, then that means you're located either here or there, right? So if you're not inside the intersection, you're located either here or you're located there. And you have to realize that because these two functions, their supports are contained in U and V, that means if you're outside the intersection, if you're here, it does not matter that f itself is not defined, because these functions, they become equal to 0. And so that allows you to define this to be equal to 0, because the transition in moving from non-zero to 0, it happens in a smooth way. And that's the whole idea behind this procedure, that you decompose a function that's only defined on the intersection as the sum, but these product functions, even though technically they're only defined on the intersection, they can be extended to a smooth function all the way on X. You just extend them by 0. And that tells you how to actually end up defining h1 of X. So how would you do this? So this is the way you would do this. You would define we define delta from h0 from the intersection to the first cohomology. The way we do that is we would then define delta of f to be equal to the following. There's two different pieces here. So we would define it, we would apply the derivative operator, the exterior derivative operator, to the first function. And this is on u intersect v. I'm sorry, on u. And then we would apply the exterior derivative operator to the other function with a negative sign. It's just like that boundary operator in the Meyer-Vitorta sequence that when you do barycentric subdivision and when you decompose a cycle as a sum of two other functions, you see, you have to understand that this is kind of like a cycle, right? Because its derivative is zero, right? Like its boundary is zero. But when you decompose it, these are not necessarily cycles because they're being multiplied by functions that are no longer constant. But together, when they add up together, they give you a cycle. So it's just like barycentric subdivision. So how do you then get a one form out of it? Well, the way you get a one form from a zero form is by applying the exterior derivative. So you take the first piece and you differentiate it. And that's going to give you something defined on U. And you can take this one and you can differentiate that one. This is, sorry about that small little mistake. I realized I should have said alpha U is defined on the intersection. That's true. However, alpha U can be extended to a smooth function on X. I meant to say it could be extended to a smooth function on V, Sorry about that. Because let me go back to the picture again. If you have a point, right, if the point is in F, this is smooth and that is smooth. But the moment you go over here, this is U and this is V, that becomes zero. And because this function is supported on this piece, as you transition from there to there, the transition that occurs is smooth. It smoothly transitions down to zero. So you're just making the function become zero as you go outside. So you define that on U. Now the point is, this function is smooth. So when you differentiate it, you end up getting something that's now going to be a one form on U. And the other piece that you have here, you're going to differentiate it with a negative sign, just like when we do barycentric subdivision. So maybe we'll write it like this. We'll write it as negative d alpha vf on V. So we have a form defined on U. We have another form, one form defined on U, a one form defined on V. And the reason why they're compatible on the intersection, the reason why these two forms, they properly agree on the intersection, has to do with the fact that alpha UF plus alpha VF, that's equal to F. So if you were to differentiate them, you would get zero. You would get df, but df, that's just zero, because we're assuming our function is locally constant, right? We're assuming the function is in the zeroth cohomology, so its derivative is zero. So that's zero. And what we see from here is we see that negative d alpha vf will give you d alpha uf. So they do agree on the overlap. So when they overlap, these two forms do agree on the overlap. So this is a coherent family of forms because they end up agreeing on the overlaps. And so delta of f will therefore give you a coherent family of one forms that's now defined on X. And that's the way that you do it. So you can, once you understand that it works for 0 and 1, it actually generalizes in the exact same way. That if you want to do this from hn to hn plus 1, right? If you want to go from here to here, then it would really be the same exact process. Instead of having f, you would have omega, and then you would take your omega and you would multiply it by a partition of unity. So everything will remain exactly the same. You're just multiplying by a partition of unity. And then the way you would define d of omega is you would just apply that to this one. And for reasons as before, these will agree on the overlap because d of omega is equal to 0. So on the overlap, it would be okay. So this is the way this map is constructed. As you can see, it's kind of fairly technical, but that's the way that it works. And I think what we can finish off on something that's quite nice, we can use this to complete the proof of the closed curve theorem by using cohomology. So let's talk about how one would do something like that. I realize that, as always, we have this tendency for the lectures to go on for way too long. So I have to give you a rushed proof of Jordan closed curve theorem. We talked about this theorem before, and we saw that when we try to prove it using homology, there were some obstacles in the way. But when you use cohomology, it becomes easier. So let me tell you what the setup of the proof is. We're going to assume that we have a function from S1 into R2. I know that in the previous version, we assumed that our function was mapping it into the sphere, but cohomology makes this a lot simpler, and there's no need for you to even work on the sphere. So you're mapping it into the plane is an embedding. So this is what we call a Jordan curve, and you let C be the image of that circle, right? This is what you call a Jordan curve. We want to show that R2 take away C has two path components, and one of which we call the inside, the other one we call the outside. To accomplish this, what we do first is we set up Jordan arcs. Now let A be F applied on the right part of the circle, right? You take the circle, the left part, I should say, and the image of that is called A, and B is the image of the right part of the embedding. Okay, so these are Jordan arcs. So the idea here is C, so this is sort of like A, and then that is going to be B, right, A and B, and they're going to overlap in 2 points, one of which you call P, one of which you call Q. So we will compute the zero-dimensional cohomology of R2 take away C and show it's a two-dimensional vector space, which will mean there's two components. Now to accomplish this, we're going to set U to be equal to R2 take away A, and V would be R2 take away B. So it's the complements of those two arcs. We use the lemma. We proved this before when we talked about the Jordan closed curve theorem, that U and V are path connected, that the complement of a Jordan arc is path connected. Right? We talked about that lemma before. Now we need another lemma. We need another lemma. And you actually had this as a homework problem. So it's basically this, that the first cohomology of the punctured of R2 take away the origin is one-dimensional and is generated by the form that omega, maybe I'll call this omega 0. The 0 just indicates the origin. This is the form. This is basically the angle function that cannot be defined globally, but when you differentiate it, you get something that is defined globally. This was negative y over x squared plus y squared dx plus y over x squared plus y squared dy. This form its derivative, if you were to take d of omega 0, its derivative becomes 0, but at the same time, this form is not the derivative of any function that is globally defined, because you want to say that this thing is the derivative of the angle function, right? This is basically what happens when you take arctangent y over x and you differentiate that. But the problem is this is not globally defined in all of that. However, this form is globally defined. So we're going to accept this. More generally, the first homology of R2, take away a point, let's say with coordinates P1, P2, would be also isomorphic to R1, and it's generated, and this is a one form that will generate for you that space. You can call that omega p, which would be negative y minus p2 over x minus p1 squared plus y minus p2 squared dx plus, I meant to say, I wrote here y, I meant to say x. So this is x minus p1 over x minus p1 squared plus y minus p2 squared dy, right? That's what happens more generally. And now you just extend the lemma to two punctures. So this is the two punctured lemma that the first homology of R2, take away 2 points from the plane, is two-dimensional. Now, this is not surprising because we do know the homology of a twice punctured plane is Z2. But the point of the lemma is to explicitly give you a basis, and it's going to be generated by omega p and omega q. So omega p, this is the shifted over angle form, and this is the other shifted over angle form. So that's the lemma. It's a two-dimensional vector space, and these will serve as a basis for that space. So that's the lemma that we need. And with this, we can go ahead and give a proof of the closed curve theorem. So this is the setup for it. I'll take this away. And previously, we used Meyer-Vittora sequence, but here it's even easier than that. You do not actually need the entire Meyer-Vittora sequence. You only need that delta map to finish the proof, and then you would be done. So we have this map that we're calling delta from H0 of the intersection to H1 of the union. The intersection of these two, that would be R2 take away C. You can think about that. And the union of those two open sets, that would be R2 take away these 2 points, P and Q. So this is where the lemma comes in, that the one homology of that union would then be generated by these two forms, omega p plus omega q, where a and b are just real scalars. It's a vector space. Okay, so this is where we're using the lemma. We're using the full understanding of what this vector space is. And now to complete the proof, so to complete the proof of Jordan closed curve theorem, we compute the nullity of delta and the rank of delta and show both are equal to 1. Then by the rank nullity theorem, the dimension of this vector space would be 1 plus 1. And then you're done. It's equal to 2. There's 2 components. Okay, so now we have to show, so kernel of delta. We claim that the kernel of delta consists of all smooth functions. Now, because we're talking about zero-dimensional cohomology on the intersection, these are locally constant functions. the kernel will consist of globally constant functions. Will consist of globally constant functions on U intersect V, i.e. constant functions on U intersect V, as opposed to locally constant functions. How do we do this? So here's how you do this. So let f be a locally constant function, and delta of f is 0 in the cohomological sense. I meant to say on the union. Yeah, it's 0 in the cohomological sense. So let's work this out. How do you find delta of f? So we're first going to write f as f times 1 times x. X, by the way, represents the union. Then we use partitions of unity. We write this as alpha u plus alpha v. So we decompose the unity function as a partition of unity. And then we have f alpha u plus, or maybe write it like this, alpha uf plus alpha vf. Okay, so we have that delta of f, it would be equal to the exterior derivative applied to alpha uf on u, and the exterior derivative applied to alpha vf on v. And we are saying that, what are we saying? We're saying that delta f is equal to 0. This is equal to 0 in the cohomology. To be 0 in the cohomology, what does that mean? It means that, i.e., there is a function, g, a smooth function, defined on u union v, right? A smooth function defined on the union, where delta f is the derivative of this globally defined function. You see, oh, I'm sorry about this. I meant to say, of course, alpha vf negative, of course. So delta of f is equal to d of g on the union. Now you can see that delta of f is the exterior derivative, but there's two separate conditions. It's not necessarily one globally defined function. And we're claiming that if this is cohomologically trivial, you can find the globally defined function on the union whose exterior derivative will agree on these two pieces. So that would mean that, so d alpha uf is dg on u, and d alpha vf is negative dg on v. Now we're going to use the fact that u and v are connected. That's the lemma with the Jordan arcs. I think I took this lemma down, right? That the lemma says that the Jordan arcs are connected. So because these are connected, these are complements of Jordan arcs, that you have a function and another function whose derivatives are equal. So that means the functions differ by a constant. Hence, alpha uf is equal to g plus some constant, and the other one, alpha vf, is equal to negative g plus some other constant. So this is on u, and this is on v. And now add these together. So alpha uf plus alpha vf would be equal to g plus c1 plus minus g plus c2. So now if you go ahead and you add them, we will get that. But this is true on u intersect v. Because if it's true on u and it's true on v, it's true on the intersection. And on the intersection, we know we can write this. So that will be c1 plus c2. But this is equal to 1. And so we see that f has to be constant on the intersection. So that's what we're getting. We're getting that the kernel of delta, the functions that are in the kernel of this map, are constant functions on the intersection. So it's just a constant. That's a one-dimensional subspace. So we have shown that the nullity is equal to 1. Now we have to show that the rank is equal to 1. So how does one do something like this? So this is what it's going to come down to is, let's remove all of this again. So so we're going to show that rank of delta is equal to 1. And once we can do that, then we're finished finally with the proof of this. So we're going to pick, so say that omega is a form in the first cohomology, and omega is delta of something, of some f. I just realized that I've used f previously for that, but whatever, it's not a big deal. And I know that previously I used f for something in there, but that's okay. That omega, so we're basically saying, suppose something is in the image of delta, right? So there's some function. So now we're no longer assuming the function is necessarily constant, rather that it's locally constant because it's an H0, not necessarily in the kernel. For some f in here. Okay, so what do we do next? Well, we can say, well, we have to go back to the way this one is being defined. So we're going to write f as f times 1, and then we can use partitions of unity to write it in this way. Okay, and then that would mean that omega would be expressible as d of alpha uf on u, or negative d alpha vf on v, right? So that's the way you can express this form. So that's the assumption that we're making about this form, that it's the exterior derivative of either this or this. So what we do next is we're going to pick a large circle that contains both P and Q. So here's a picture. Here's P, here's Q, here's a Jordan arc that we're calling A, here's another Jordan arc that we're calling B. And we're just choosing a large circle that contains both P and Q. Contains inside, right? They're inside, that are inside the circle. So then, what would happen if you were to integrate over the circle? So you're integrating a one form over a one chain. So think of the circle as a one chain, as a closed one chain. So what would happen when you do that? Well, you see, omega, u is the complement of the red one. And you can see that the circle is contained in the complement of the red one. So that would be the same thing as integrating d alpha uf. Right? That's what that would be. You can also say it's negative d alpha v. That is correct. I mean, you can use both of them. It does not matter. And when you do that, you get that this is equal to, and this is where you use Stokes' theorem, that this is the integral of alpha uf on the boundary of C. But the boundary of C is 0 because this is a closed chain. So that ends up being 0. So this shows that integrating over circles results in 0. Okay, but what do we know about omega? We know that omega is equal to this, right? I'm sorry, omega is equal to this, but we also know something else. We also know that omega is a linear combination of these two, because this is the description for the first cohomology. But we also know, so let's write this down. But we also know that omega is, I guess I should say equivalent to, because in cohomology you work up to equivalence classes, that it's equivalent to a linear combination of those two angle forms that we mentioned from before. So then when you integrate over this circle C, omega, that would be the integral over C, and then that would be A omega P plus B omega Q. So that would be A integral C of omega P plus B integral C of omega Q. So you're basically integrating the derivative of the angle function as you wind around the circle. And as you go around the circle, the change in the angle is 2 pi times the number of times you go around. So in the end, you're going to get that this is equal to A times 2 pi plus B times 2 pi. And so, but that's supposed to be equal to 0, right? Because we've said that this integral has to be 0. So that's supposed to be equal to 0. So canceling away the 2 pi, we find that hence A plus B is equal to 0. Okay? So basically, so what did we show? So to summarize, we showed that if omega, if you have something in the first cohomology, and omega is in the image of this delta map, then omega must necessarily have the form A omega P plus B omega Q, with the condition that the sum of the coefficients adds up to 0. So the rank is, so the image of delta is the subspace of this vector space with the additional constraint that the sum of the coefficients have to add up to 0. So the cohomology has, so these are just arbitrary linear combinations of these two forms. But the image space, the image subspace, has the additional constraint that the coefficients have to add up to 0. So in other words, it's a one-dimensional subspace. It is a one-dimensional subspace, right? Because this is a two-dimensional space, and that's a one-dimensional constraint. So the image is a one-dimensional subspace. So that completes the proof. The rank of delta is 1, the nullity of delta is 1, and then finally the proof is 1 plus 1 is equal to 2. There's two components, and that is the Jordan closed curve theorem.